All right. So we're going to do modeling, and basically we I don't know, the book keeps on showing this picture, which is the first picture we looked at in the book, and it's all about the different processes you go through when you're dealing with data, and what you want to do with your data. So we've done the transformation with all those functions. We've also done the visualization, which was I think one of the early chapters, but mostly I think transformation and the tricks to deal with transformation. And now we're going to look at some kind of modeling, not all the modeling bit, but at least the basics to get us running, which will be more of like the modeling to support the visualization. So that's why the book actually talks about things like exploration of the data rather than doing confirmation of, for example, hypothesis, which is also fun to start with, not to deal with the hard stuff. Okay, so some things I'm going to just talk about some of the things that you need to know when you're working with models, both in R and econometrics. So basically, all you need to know is that there is different families of models, and here they simply put it as you can have either a linear model or exponential model, or quadratic model, or polynomial model, whatever you want to deal with. And you can also have things like logistic regression, which can also be a form of, which can be estimated as a linear model if you want to do that. But then when you have a specific model that you want to fit your data to, then you actually estimate some kind of parameters for that. Yeah, so basically that's why you have initially things like this. A1,
Hello.
A2, yes?
Oh, okay. I was talking before. Maybe you can hear me, right?
No, we couldn't hear you.
All right. I'm so sorry. So please, can you go back to the previous introduction of the program? I was talking, and I want to ask question.
Okay. Hold on. Let's first go back. Oh, where was that? Okay, here. You mean here?
Yeah, go down, please. Right. So yeah, here. So I know in machine learning in Python, we were saying the 60%, this is cross validation, something like that. We have training, test set, and validation set, right?
Yeah.
But this terminology here, it seems somehow interchanged. Please, can you explain? I'm not sure about which one is query. Yeah.
Yeah, so I think the training and the set is the same. In Python, I remember, okay, mainly machine learning, also like in scikit-learn or something like that. They use a different terminology from query. But how I can explain this
Yeah.
is basically the same thing. So you have the training, here they're using a 60-20-20 a split of the data set, but it's not really a given, especially for the query. Sometimes you could skip the query data set. So basically the training is the one you use to estimate your parameters or coefficients in the model. And then you go to the query where which you can use to compare some models and maybe select the best model and do some stuff in between there. The test is going to be the one you use to see how your model performs when you give it new data. So that's why the test data should be different from the training data. And this is used to test things like overfitting or underfitting, stuff like that.
So I think in machine learning, what they call the first one is training set, the second one is tested, and the third one I think is it validation set, something like that, if I'm not mistaken. Yeah, and this percentage are they gold standards of division of data, or we have some way to leverage how we define based on our intuition, or is it the gold standard 60-20-20?
No. So basically, this is a rule of thumb, more of like to get you started, but the percentages depend on your data. For example, the best example I can give you is that if you're dealing with machine learning, normally you're dealing with large sums of large data sets. So you might find that a 20% of 10 million rows of data is not really, is really going to be so big, and you're going to lose the power to better estimate or train your model. So you might even be better off to just increase the training data percentage and just remain with a less data percentage for the test, maybe 10%, something like that. So it's you when you are unsure, you can just start with these values. Some people do like they skip the query part and do like 70% training and 30% testing. That's also okay. So you'll see different percentages actually in different books for econometrics. Even machine learning, you see different percentages.
Okay, good.
All right. So here, basically, the good thing about the modeling they present in this book is that they try to actually show you how you can combine the visualization and the modeling, which is their target. And the target is basically to use the models for exploration, to reveal to you some patterns that you could find in the data, or relationships between two variables in the data. And so the thing I need to start with, or something I need to introduce, is we've seen tidyverse, but we've also we haven't seen or worked with this package called Model R, and that it's really actually important to try out if you want to test out different things. So for example, actually, I didn't know it existed, but based on the things that they do with it in the book, it's very easy to work with and helps you move faster. So it's something to actually check out. Yeah, so anyway, but basically, this picture here gives you a whole idea about modeling. So for example, if you have if you have a data set called SIM, and you have data points, which are the dots here, you could try out different lines. So here they're doing a simple linear regression, simple because it only has one variable, one dependent variable X, and one independent variable X, and one dependent variable Y. So basically, what we're trying to do in modeling is to find the best fit. So which of these lines is the best to match the data? And how do we define the best? When we're defining the best, then we move to things like minimizing the distance between the model data and the actual data. So that's why you keep on seeing things like prediction and the actual value normally, which here they're calling the response. So things like this, we're trying to minimize the distance, the total distance from the response, which is this dot here, and the modeled or prediction, which is along this line. So basically, what we're doing here is that we're trying to find a relationship, and we need to find out whether the relationship is the best or not. And that lets us compare different models. So basically, the thing is that you can do this manually, but we don't really have to, because in R, we have a written function that can do this for us. And I'm going to skip this part here a little bit, and we'll come back to it, I think, in some of the exercises. Then I think I'll go through them again. So
yeah, Alan, the ones that you are saying you want to skip, they are basically trying to show us how the modeling works, right?
Yes.
Yeah, bit by bit, they are adding small details and see what really happens along the way. But this is not what we would be doing at the end of the day, right? If you want to do modeling.
No, actually you do, because it depends on
I
your
thought
data
you
set.
only need to take the functions and stuff like that to generate the modeling prediction and stuff like that. Do we need to do all those steps?
Okay. So basically, all you need to do, all you need to know is that you don't need to worry about it now, but you are better off with you doing it later on, if need be. Because right now we're dealing with play data, and it's really fine. You might just run the model, get the results, and you continue. You don't have to do all this or try out different values. But for example, there is a different realm of modeling whereby you are constraining the parameter. You want a parameter to be in a given range, or you want a parameter to be a given value. I mean, a parameter, a coefficient you are estimating to be a given value. Then you actually need to know these kind of tricks, under the hood, so that you try them out yourself. But for now, I think if someone is starting with modeling, they don't need to really worry about this. They just need to be able to see some result and start small, and you can always come back to this and see if you want to try out something. I hope I answered your question right.
Yeah, sure, Alan.
All right, so the same thing that they're trying to show here, trying to select the best model and blah, blah, blah. So we'll return to this, I think, a little bit. But just one thing you need to note is that later on, when you're trying to play around with your model, things like grid, expand grid and stuff like that, they can be handy when you're trying out different types of models, mainly because this just helps you generate values very fast, and you can try them out also very fast. So it's nothing really fancy or something to be scared about here. It's just a way to generate values and put them in a data frame. All right, so right now I'm looking at the linear regression. So basically here, when you're trying to, instead of trying out different lines, you could actually optimize the selection. And you can optimize the selection with different algorithms, that, for example, minimize a certain value. In this case, they could be minimizing the absolute mean for between the absolute mean deviation between the prediction and the response value. Here they're talking about a Newton-Raphson method, but there is different methods. So anyway, what you need to do is this is another variable that comes with R. I mean, another function that comes with R, and it is it is called Optim, or optimization, whatever you want to call it. But it takes starting values and takes a measure of a function that needs to be used as a reference for testing optimality or convergence. Then it also takes extra values. So if you look at it, actually it has, I need to check it out. Yeah, so this is the Optim function, basically, and there's dots here which take arguments to be passed to the function, which is going to be used for example, finding out whether something has been minimized or reached convergence in this case. So here, it's well described anyway. We can check it out later on. So now I need to go back. Okay, so I also try to jump through this, but maybe we can return to it later on. But the basic part from here until backwards in the book is basically just showing that you can do this manually by yourself, but you don't have to do it manually if you don't need to.
Yeah, Alan.
Yes?
I have a question. The above Optim arguments, can you go? Can you go up? Yeah.
Sorry, what did you say? Can you come again?
This Optim, the Optim function.
Yeah.
Can you hear me?
Yes, I can hear you.
Okay. I'm talking about the Optim function. So we have the first argument, which is a vector, which is these two values vector. We want to find the optimized point between these 2 points. What is this major distance? What is this C?
Yeah, so this measure distance is actually if it is a function which we have created.
Okay.
And inside this function, it has I can just show you just a little bit. It has, so this is measure distance.
Oh, I see.
Yeah, it's here. So inside measure distance, we do the modeling and predict. Then after modeling, after predicting, we get the difference. And after getting the difference, we get here we're calculating the root mean square error.
I see.
Yeah.
Okay, go on.
All right. So basically, what they're saying is that you can just have an inbuilt function, which is LM in this case, and pass on the family of function, the specific family of functions. Here, they're using a linear model and the data. And after that, it will give us actually the coefficients.
Yeah.
For example.
Sorry, I have many questions because I like this part, but I don't know it. So this y tilde sign x represents linear function, right?
Yes.
But what about if we have maybe ax squared plus cx squared cubic squared and cubic? How do we represent it?
So basically, I'm going to try and answer that in a way and see if it works. Let me try to open up my and try out NLP. Okay. All right. Okay, so basically this is what we have, right? And you can, it can run. But what you're saying is that if you have, for example, that, right? Hello?
Yes, Alan.
Okay, so this is something I've never really tried, but it seems to work. However much it might be a bad idea to do. Yeah, anyway, it works.
But it's not linear, right?
No, it's not gonna be linear, of course. So it's not the best way to actually model, of course, that kind of relationship. But it will work because what R does is that I need to. What R does is it first produces a matrix with y and x squared. If you get what I mean. So it will work. However, it will not produce the best the best estimates. So definitely it will work, no problem. But it won't be the best estimate of the parameters.
Yeah. So my question is, this kind of presentation is called linear model. Is that if I'm right?
Yes.
But when we put something like this, it becomes is this model or cubic model, or it's not a linear, but rather it's no longer linear. So can we represent non-linear function in a linear fashion?
Yeah, exactly. So that's why this is able to work. So basically, you can of course we can linearize anything, pretty much most of them, very many of them. Okay, or estimate them with linearization. But I think the key part here is that you can actually, I mean, since we can linearize anything or represent something that is not linear in linear form, we can then use the linear estimation to get to get the parameters.
Right.
Yeah, so that's what R is counting on here. So it can do that, but when it does that, it's going to be an estimation, an approximation rather than an exact measurement.
But everything is approximation. I mean, even the linear.
Yeah, that's true.
Yeah, I mean, all we're doing is everything is just trying to approximate to, I mean, none of them is true, you know what I mean?
Yeah, that's true. That's true. It's just that some approximations are worse than others.
Yeah, that's what they said. Yeah.
Yeah, but yeah, so this is perfect. It's actually quite nice to know. But because so from here, just to before I continue, what you know is that R gets this and creates a data, a matrix of x squared.
Okay.
Yeah, of x squared itself, rather than solving it like this.
Basically, so put s cube. Let's see cube.
Yeah,
it's linear in the sense that each component is combined linearly. So if you had x squared plus x cubed, it doesn't matter that those things have powers, just that the coefficients in front of them, or like the contribution of each variable will be linearly combined.
Yeah.
That's what makes it a linear model.
But I have a question. What do we mean by if we say a function is linear? What does that mean if we say a function is linear?
So you're trying to basically find what coefficients can you put in front of x cubed to make this model fit the best way it can. If you had another component, let's say x squared and x cubed, then you'd combine them linearly, i.e. find x squared, find x cubed, and then find coefficients such that when you multiply coefficient 1 with x squared plus coefficient 2 times x cubed, you're trying to approximate y. So it's linear because you are treating this x squared or x cubed or x as like an individual item, and then you're finding coefficients to put in front of them and just add them together.
Okay, so what is an example of nonlinear function?
What is the word?
An example of nonlinear function.
So basically what, let me see if I can understand your question.
Ava, do you understand my question?
I do understand your question. I can't think of one off the top of my head, but the reason why you can have y tilde x squared and still have a linear model is that you're trying to find the coefficient. You're treating x squared as, let's say, call it, I don't know, z, and you're fitting the model on y is explained by z.
Yeah, I got you. Yeah.
Yeah. So here, however much you are specifying a nonlinear formulation, it is calculated and turned into a linear kind of formulation because the data is pre-processed for that. Yeah. So yeah, but anyway, that means that with these estimates, or for when you're running the models, you can even do things like log x, or of course it's what log x you can do like this, like log of x. You can do that. You can even add like x again and see what happens and stuff like that. So everything is gonna work, but of course you need to do it with caution because not everything is going to make sense.
Yeah. So is this also true when we say, okay, here we are talking about models, linear models, but is it also, when we say linear function and nonlinear function, are they the same as linear? Do they have the same notion about linear model and nonlinear models? Because when we say a linear function, given a function is something that is linear, but when we say a function is non-linear, obviously we know that a function that is some kind of squared function or cubic function. I mean, literally in mathematics, that is what we call nonlinear function. So do they have the same notion, or they have different notion in terms of modeling?
So they have the same, they have the same notion as in mathematics, because the modeling is actually matrix algebra. How they estimate the parameters, it's matrix algebra, and everything is based on mathematics. So it is the same notion. You should always think about it the same way you think about it from mathematics.
Okay.
And this is not going into the estimation.
Right, good, okay.
Yeah. So if you have a good, strong, if you have a strong mathematical background, then it kind of becomes a little bit easier for you to do specification of these functions.
Mm-hmm.
Because you know what everything means when you write it. All right. So now we could go through some exercises. Then I think what I suggest is that I will try to explain most of the things, which some of which I've skipped, and then if you have any questions, you can ask and we discuss them. All right, so here there is 3 questions for the first exercise. And they're saying that one of the downsides of linear modeling or linear models is that it is sensitive to unusual values because the distance incorporates a square term. And the distance here is the error. For example, the distance between the predicted and the response. So they're saying that fit a linear model to the simulated data below, this data, and visualize the results, then rerun a few times to generate different simulated data sets. What do you notice about the model? And yeah, this was quite a silly exercise. But yeah, anyway, so this is what I did. So I have this data, and which is the same that was given to us. So basically what they're doing here is they're generating the X values. And from the X values, they're generating 30 of these. And for each of the X values, they multiply it by 1.5, then add 6, then add this, which is a T distribution, more of like a sample, an additional error, if you might say. And yes, so they want us to do modeling for that. So what I did was I have my LM, which is a function to do linear modeling in R. So I have my function, my family of function, which is a linear model I specify, that is y is equal to a plus b x in this case, and my data, which is the simulated data up there. Yeah, so basically what I did, I could, after running this, it becomes like a list of different components. So if I might just, I don't know whether I could run it here. Yeah, so when you run a sim mod, it's actually should be even more than this. When I run sim mod, it gives you only this, but it is inside there is more stuff than just this. Because from there, from sim mode, we can actually do like a summary. Like that. So it's quite a lot of things actually you can find, not just the one that is output when you run sim mode. So just to show you what's happening. So it's more like a summary of the model and things like R squared, P values, blah, blah, blah. We can look at those later.
Yeah, Alan, a quick one.
Yep.
So regarding this linear and linear, I just Google what I did right now. I find out when they are talking about linear, they are not talking about the independent variable like x. So if we have ax squared plus bx, what they are talking about linear is a and b. I mean the parameters, they are linear. So we can have ax power 5 plus ax power 6. So all these are linear. So it is that parameter that is linear. It is not what I'm thinking when we have x squared, x power 5 is not linear. That is not the part they are talking about, the linearity. So I share a link that they explain about that. So thank you for good discussion to clear the doubt.
Yeah, but also here, actually, to be specific, they are talking about linearity in both the variables and the parameters.
Mm.
Yeah, so yeah, we shall continue that later. That's a long discussion about identifying nonlinear models and stuff. Okay, so yes, after this, just to show you, this is how the results look like, and it's very challenging actually to think about what they're saying if you haven't really sat down to think about them. But it's nothing to be scared about.
I'm scared about it, Alan.
Are you scared?
Yes.
That's a good thing. That's good.
Yeah, help me.
Okay. Okay, so basically here, I'll start with the way I learned this, just to look at the important stuff.
Okay.
What you need to know is, what you need to run to is the coefficient, this part here. And you know that you have the intercept, that is your, and give me a second here, please. I need to run this model again so that I'm not getting the logarithm there. All right. So, oops. Okay, so this is the result we have. It's a simple model. That is y is equal to a plus bx. So here what we see is that we have the intercept, which is our a, and it's 6 here. And the x, the coefficient, which is the b, is now 1.3. So here you only look at the size and you look at the signs. For example, here it is a positive relationship between x and y, because this is positive. If it was negative, then of course that's a negative relationship. The intercept is not really that interesting most of the time, depending on the field that you work with. But sometimes you could also just take it as something, a value that you can use when all the other variables, the predictors, which is the x, for example, here is 0. What is the value of y? It could also be like the mean or the average value of your y. And another thing you need to look at here, with so that we don't have so much stuff, is this one here, the adjusted r squared. And this you can take as a form of how best your x explains the y, and it ranges from 0 to 1. So the higher it is, the better your model is most of the time. So that's a quick. Those are some quick details about what to look at when you see this. So skip these revenue stuff, residue stuff. It's important, but you can just skip it for starters. Just look at this estimate, then look at your r squared. You start from there, then you build onto that.
So what will tell me that my model is good?
Yeah, so there are so many different things that that can tell you that your model is good. It's not just a single parameter. But the first one is this one here, the adjusted R square. That's one of them.
Okay.
Your general model, of course. Then of course we're going to look at another one, which is root mean square error. And actually, before I go into the root mean square error, yeah, this first, let me just say the first one is the adjusted R square. Then you can look at things like, if you want, the best thing is to look at the residues. For example, start with the residues, especially if you're going to do predictions.
Okay.
So your model is good based on the purpose that it wants to do. So if you're trying to look at predictions, then you jump into the residues and see how the residues behave. And we're going to look into that actually because the book also talks about it. But okay, if your model has a purpose of finding out relationships, then the signs, for example, matter. You know, you can't say generally that, for example, prices higher prices are going to lead to people purchasing more items, because from normal economics we know that higher prices lead to less demand, stuff like that. So things like that you need to look out for. Then also you need to look at what they call significance, these things here, and you can read out them just there. Normally, a quick one in R, if you see some stars, that's some good sign. If you see no star, then that's scary in simple terms. But yeah, so those are the things that I can give you right now. But there's so many other things that some other metrics that you need to look out for, and some maybe we'll be finding inside here in this chapter. Sounds good?
Yeah.
Okay, so now let's first go back to this question. So they want us to just fit the model and see what changes based on submitted data. Basically here, what I did was to fit the model and just plot, put out the results and just plot the predicted or estimated line, this one here. And basically, if you run it again, since we simulate the data again and add some error or noise, then everything is going to change. So if I run it again, I get 6.48, 1 point blah, blah, blah. And if I run it again, it's going to be something different. So if you just look at this one here, this value here, which is 6.48, if I run it again, should be different. So like that. It's now 5.79, and that's what they wanted us to find out. So it wasn't much of a fun exercise there, just to see changes, just to get comfortable with working with the modeling bit. So any questions about that?
No, thank you.
Not for me.
All right, now the second question is they're saying that one way to make linear models more robust is to use different distance measure. So the distance measure they're referring to is the measure of the error term, or the difference between the predicted and the response. So predicted is the values normally are along this line, and the response are the dots that we see up here. So previously in the book, earlier in the book, they defined this distance measure as root mean square error. Now they want us to try and use mean absolute error. And the difference is that here, you take the difference between the actual value and the predicted value. And you take the absolute value for that, because I mean, the model is going to be either up or down, just like we've seen those, just like we've seen these dots. Some of them are up, others are down. So after doing that, we get the average. And you can say that on average, my model is off by this amount. So that's how you can interpret the mean absolute difference. So we're not really stating up or down. In this case, we're just saying on average, this is how much I'm going to be off if I use this model, for example, for prediction. And the good thing about so this one is good because you can interpret it like that, for example. But there is another one here. The other one they used in the book was root mean square error. Similar concept is just that instead of using just the absolute, just the mean, they first do, I need to look for it. Where was it? Yeah, here. They first square it, which is more like almost like taking the absolute value in a way. Then you take the mean and take the square root for that. So they're different measures. That's what that's what they're trying to show us here to measure a deviation. But you're good to go if you just use like root mean square error. It's quite common. You can also use the mean absolute error.
Yeah, a quick question, Alan.
Yes.
So which one should you use? And they have different scenarios, right? I mean, I quite remember sometimes one among them is good for detecting outliers or some stuff like that. I'm not quite sure.
So, yeah, so that's a big question. I think a big discussion actually people have looked at, and I don't really quite remember the discussion fully. So I can't really answer that actually about which one detects outliers most. I can't really answer that for you.
Yeah. I have something here, just Googling what they said, the difference. They said taking the square root of average of squared error has some interesting application for root mean square error. Since the errors are squared before they are average, the root mean square gives a relatively high weight to large errors.
Mm-hmm.
This means the root mean square should be more useful when large errors are particularly undesirable. The three table, yeah. So I mean, I read something, but I cannot. This is a Medium article. I just Google. I think they did a comparison between the two. So it's good if one would like to read about it. I will go back and read it and understand which ones to use in which particular cases. But this is the point that I highlighted. Is the write some differences between the two.
Mm-hmm. Yeah, and that is true. There are differences. So normally you find that since if you don't want to go into the argument of which one to use or not, people use like about 3 of these measures, and then try to make conclusions based on those. So that's one way to deal with it if you don't want to, go into all the details of like, do I want big errors? Do I want small errors? Which one is better? You can just base your decision based on like 3 of these measures or 4 of them if you want.
Yeah, so yeah, this is a good question. So I find one sentence in the article that I like. They said the root mean square has the benefit of penalizing large errors. Mm-hmm. So if you have large errors, which are basically an outlier, so it will quite useful to use them so that they can quickly flag outliers. I think this is the thing that I was interested before.
Yeah.
Okay, cool.
Yeah, makes sense. Yeah, so okay, so basically what we wanted us to do is that just instead of using the root mean square error, we use mean absolute error. Or like actually so your question was, or even what you found out from Medium is very additional to this, understanding this part here, where they're wanting us to use mean absolute error.
Yeah, another question, Alan. Don't we have functions that they will calculate this root mean square and m in R that we don't need to write this function? That do you understand my question? Do you have?
Yes, there is functions actually. I haven't really used them. Yeah, I don't really remember them. I normally just calculate them like this myself. So yeah, but there should be functions. People have put functions that do this for you. I haven't really actually, I don't remember them. How about you? Have you used any of those functions?
No, not in particular, but I mean, it's a simple enough function to define. It's 2 lines of code.
Yeah. So normally for me, I always do it myself because I want to I want to try and go through the predictions themselves and also plot them and see what happens. So it's always quick for me to just calculate it like with one line like this.
Yeah, and also just another point, like if you want it to be even more robust to outliers, instead of taking the mean, you can use median, which again, in general is more robust in terms of, you know, sensitivity to outliers than means.
Yeah.
So if you want to take it to the next sort of level, you can use median instead of mean.
I don't know, but for actually, this is the mean absolute error is something I've never used like in my work. I find it like, I don't know, I find it a bit useless for me.
I think I have used mean absolute error, you know, and I think I share the function. Yeah, I have used it before, the MAE, yeah, which actually has 2 arguments, the actual and predicted value. Yeah. Yeah, however, you said median can be used to, is it also used to measure the difference between the performance of model? Because we are talking about model measures, right? So you said one way to deal with outliers or errors is median. So does that mean median is used to measure the model performance? Because this parameter root mean square and mean square error, they are used to measure model performance, if I'm right?
Yeah, so in line 158, instead of mean of absolute difference, you could median of absolute difference. And
I get it.
Yeah.
Gotcha.
I mean, you can, you know, there's nothing sort of tying you to either root mean squared error or these. You can define your own function. You can, I don't know, you can take the mean of the interquartile range if you want, or whatever. Like, you can basically, having this sort of optim function means that you can define an arbitrary sort of distance measurement and use that to decide on what's a better model.
Right. So based on experience, however, which one do you find is more better to you? Which one have people have been using maybe in literature or in modeling? You guys with experience, which one mostly been used?
Like you said previously, if there are a lot of outliers, error isn't going to be that.
Right. Okay, cool. All right. Don't be offended with me today. I'm having many questions because I like the topic.
I'm not offended.
No worries.
No, not you. I mean, I'm just asking many questions.
No worries. All right. Yeah, so this one here was also basically similar. So what I did was to use Optim. I think that's what they suggested actually, and plotted the data. So basically, it's like doing a linear regression also, just like instead of using the mean absolute error as a measure of convergence, I mean, instead of using the root mean square error as a measure of convergence, they're using the mean absolute error. What did I do? What's the error? That's weird. Okay. I'm getting an error I don't understand from where. Okay. Does anyone see where this error is coming from?
So it looks like, well, function cannot be evaluated at initial parameters.
Okay, that's weird. No problem. Let me run everything from scratch. Okay. Oof. So weird. All right, seems to work now. Oh, okay, yeah. So basically, I did the two models, and the blue was the one we had before, but we're using the simulated data now. And do they have the same things? Whoa, nice. Oh, weird.
No, they can't. If they had the same things, they'd be on top of one another.
Yeah.
Maybe it's something in the plotting?
Yes, weird.
Yeah.
That's so weird. What the heck? That's so weird.
Do you want to go up to the cell so we can see?
Yeah.
Okay.
Okay.
It's SimMod 1 in both of the text calls.
Yeah.
If you scroll down a little bit. So in line 177 and 180 something, if you scroll down a little bit, you have the same text, like 177 and 183. Do you see? Coef underscore sim1 underscore mod 1, comma 2.
That's so weird. Why did I do that? Okay, that's so weird. All right, no
But yeah,
problem.
we can see that it's different metrics give different fits.
Yeah, no worries. This is the green one, and it is the MAE model. That's weird. Ha. I think I see what happened. All right, let's run this again. Oh.
Yeah.
Much better. Yeah, that's weird. When did I change that?
I don't know.
Oh God. Okay, cool. So still don't, this wasn't fun for me, actually. But well, yeah, it was more of like, oh, you can visualize stuff from the model. Yeah. And we can also do median and see what happens.
Yeah.
Oh, where to do?
Oh yeah.
Okay, let's do that here. New function. Median. All right. So, yeah, right. And don't do that. Okay. I need to add a line. Yeah. I don't know where to put this. 5 maybe. Oops. X should be 5. Let's just do that and see. Ha. Okay, let's put this as red. It's too much danger. Oh, that's weird.
We need the ab line as well.
Oh yeah.
I feel like we could have used the PMAP here.
Yeah, that's right. Yeah, very true.
Yeah, so we need to use the PMAP.
Maybe next time. But it turns out the median isn't that good.
Yeah, I mean, this is one of the important, I mean, to fit any redundancy, you know?
Interesting.
So which one is red? Which one is the blue?
So here, the blue is the one, the linear one, which is basically using root mean square error. And then the red one is this using the median absolute error. Then the green is mean absolute error.
So which one is looking better?
Can't really decide between the mean absolute error and the root mean square error one, but at least the median is not so good.
Well, it looks like, so the initial values were 6 and 1.5. So it looks like the root mean squared error is a little bit better. In terms of how it looks.
The mean absolute error?
No, the other one, because it's 5.79, which is closer to 6 than 5.5.
True. From the initial one, yeah. Like the average of the y's.
Yeah, whereas the gradient is better with the mean absolute error. So I guess it depends on what matters more.
True, correct.
Cool.
Nice. All right, so yeah, maybe we'll end on this one here.
Yeah.
The last question.
Okay.
Yeah. So yeah, the last question is they're saying that one challenge with performing numerical optimization is that it's only guaranteed to find one local optimum. What's the problem with optimizing a 3-parameter model like this one here? So this model would have 3 parameters, A1, A2, and A3. Basically, it has 3 constants, as you can see. So it's the same as having, I don't know why they did it like that. But yeah, this makes a difference if you're running it with Optimum. Anyway, but if you're running it in with LM, it's going to be combined. The A1 and A3 are going to be combined. So anyway, so what I did was just to run this model, use it in the measure distance function that we have, and use Optimum. Then give it 3 starting points for our values here, and our data. I just use the simulation data again here. So if I run this, it's, I don't know, it's just really silly, but you can't really find anything from running this. But what you could do is that, because when I tried to run it again, it was giving me the same values anyway. But if you think about it from optimality and optimization and mathematics point of view, the point is that if you're having more dimensions, if you're adding more dimensions on the data set or on the function, then you are more likely going to end up with multiple optima. So if multiple optima in this case, I'm implying that you could find different combinations of A1 and A3, for example. In this case, I don't think we're reaching that we're having that problem because, like you see, when I run it, it's returning the same value every time.
It's interesting.
Yeah. Okay. Right. So I think we can stop here.
Yeah, sounds good.
Yeah, then next time we shall go through some visualizing of the models, which is actually about, understanding how to pick the best model, kind of like that.
Mm-hmm.
Cool. Who is expected to do the next chapter? So if no one has picked, I will try to pick the next one.
Okay, you can take it up. No problem.
Okay.
You mean
Right.
model building, right?
Yeah.
Yeah. So so you'll be after I finish the second part of this.
Yeah.
Cool.
Thank you.
Okay, so we're going to continue with the modeling chapter. So last time we did some bit of introduction and we did some kind of simple modeling, which was basically trying to see what happens under the hood of the different modeling or one modeling function in R. Basically, we could actually do it ourselves, but why should we do that if there is other functions in R that can do that for us? So we also noted that there is different model families. So you can have a linear function specified for your model fitting. Then you can also have, for example, like a nonlinear, whatever kind of nonlinear things that you can have. So one interesting thing that we saw last time was this modeling package, Model R. It was my first time to use it actually, but it's pretty cool. Should have known about this when I was doing my master's thesis. Then, okay, so we did all the simple modeling and did some exercises. And what we're going to do next was visualizing the models. So we visualizing the models, there is just a few things that we might need to use later on. And one of them is the data grid. So data grid is part of our model R function, as you can see here. And basically it helps you create some kind of simulate data. I think simulate is the right word. So for example, if you have like X variable is between 1 and 5, then it gets the unique values for X, and for X, then it generates all the possible values for X. That wouldn't be interesting, of course, but it becomes more interesting when you have two variables. So it creates all the possible combinations of the two variables. But anyway, so when you're dealing with visualizing models, or when you're trying to dig under the hood and try to see what's really happening, how is your data behaving when it comes to a certain model, you need to, it depends on your reason as to why you're doing this. So it could be data exploration or explaining the data. It could also be some kind of prediction. Shamsuddin, are you putting up your hand?
Yes, Alan. So yeah, so this under visualization, the model, he said we are going to focus on understanding a model by looking at its predictions.
Not really understanding. I mean, the examples are going to be about predictions, really, but you can use them to also look at relationships in the data.
Mm-hmm.
Whether your data, whether your model is actually capturing some kind of relationships in the data.
So using model, we can do many things. One of them is prediction, right? And the other one is trying to find the relationship between some variables in your data, right?
Yeah, so there is more of like finding relationships or explaining the
explaining
in the data.
Okay.
It could also be things like hypothesis testing.
Okay, yeah, I gotcha.
Yeah. So yeah, basically what we need to know here is the data grid function. So it's really good to generate like So for example, we looked at some kind of testing the data and also training, training the data and testing. So you could use this to test your model, for example, this data grid, come up with quick data sets to use. So then, of course, we're also going to see something to do with ad predictions, which is also part of the model R package. So ad predictions, basically, you give it a model and the data, then it outputs the prediction to your data set. It's under the column called pred in this case. So in the same way, it can also add residues.
Yes, Alan. So why don't we work on the model, on the real data? Why do we use on the grid data? Why can't we use on the real data that we have before?
So basically, of course, normally it should be the real data, but the actual thing that it's doing with the grid actually in this case, which was called data grid, it is getting the possible values that could happen.
Gotcha.
It's not that you're coming up with data sets out of the blue.
Yeah, gotcha. So expected points where the answers may lie within, right?
Yeah, exactly.
Okay, so we actually trim down the search criteria to the large possible values. We narrow down the search area where our points are, right?
Yeah, no, not really narrowing it down, because this can actually grow exponentially in terms of the combinations that you can have. If you have, for example, 2 variables, it can really grow exponentially. Yes, so now, so what we'll look at is the predictions and the residues. Then we'll see what happens actually, how our model is performing. So I'm going to jump to the exercises, then we'll be visiting some of the things that I might have skipped. So the first exercise, this one here, it's about using the LM function, which is about doing linear modeling. And basically what they want us to fit to use LOESS, which is another function which fits a smooth curve. So instead of doing the LM to fit the model, we fit actually a smooth curve. Then we repeat the process of model fitting, grid generation, predictions, and adding maybe residues and stuff like that. Then we visualize everything. So we sort of like compare the 2 models using visualization and see which one performs better. So we compare both of them. So okay. Can you see our studio?
Yeah.
All right. So so here I'm going to go with the LO. I don't know how to pronounce it in short. LOESS function, which fits a smooth curve. Basically here, I never used this function really, but it's already documented online on CRAN, for example. But this is how it works. It works the same way as the LM method. So you just do LOS, identify the function, or the formula which is turned into a function, and the data. When you do that, however, I found that this function here, LOS, does not really behave the same way as LM. For example, you couldn't really do summary. I couldn't really get that out of it. But anyway, we didn't really want to do that for this case. So we estimate the model like that. And then the next step is for us to add some predictions. So what I did, I generated the grid based on the X variable in SM1. So of course, it's always good to look at your data set. So what I can do here is I could we just have a look at our data and see what it looks like. So this is our data set. Of course, ignore this residue here. It was added on previously when I was doing stuff. So our original data is X and Y, and this is our X, this is our Y. And I think we can also do maybe count. Count X. Let's see. Yeah. So 10 values, and these are the frequencies for those values, basically. So what grid does, it basically is going to give us values from 1 to 10 inclusive. And I can also do that for us and see what happens to it. Grid X, data grid. So basically, that's what it gives us, because it gets the unique values of X and generates all the possibilities. Well, none so fun. Yeah. All right, cool. So after I generate the grid, then I just want to see the predictions produced by our LOESS model. And this is how I do it from the model R package. Our next step is, sorry?
No, continue, go on. So
then of course, after that, so after you do the modeling, you get some predictions, then you want to see how the model is performing. That's the use of the visualization. So what I'm doing here is just to show how the model is performing using visualization. So I have my data and I plot the X value. So basically I'm starting to plot the original data, which is the X and the Y. So I'm plotting the X against the Y with those lines. So just the points. Then on top of that, I want to compare two models. One produced by yeah. Now I want to compare two things. I want to compare the results produced by the LOESS model that we've estimated, and also the geom smooth what's it called, layer or whatever, the geom smooth something in a ggplot basically. So we want to see how different they are in a way. Of course, if you want here, you can also add the LM function if you want. But anyway, so what I did here was the geom smooth is in a certain color, which should be about I think light green or something like that, light blue. Then I put the geom line. I used the geom line to indicate our predictions with our LOESS model. And I'm making this dash just to be able to see the differences. And it's in light red. So yeah, I can just rerun that again and see. So basically, this is what we output. And it's, of course, it's very nice that actually right now R gives us this message. I mean, we're doing the same thing. That's why the lines are sort of like overlaid over the other. So just a realization that actually geom smooth uses the LOESS function that we have done ourselves. So, and of course, if you want here, you could remove the from geom smooth. You could remove the confidence intervals. To basically be the same thing, but without these gray areas.
Calendar reminder.
Does it work?
Your false needs to be all uppercase or just capital F.
Oh yeah, yeah. Oh, so picky. Yeah, but then we get something like that. But in predictions, normally the standard errors are sometimes useful. So you can choose whatever you want. So anyway, basically these two functions, if you do if you just do the geom smooth, it's going to give you the same results as doing the predictions with the LOESS model. All right. So basically, I think here what I was doing was I was still trying to compare the results of the the quality of predictions for the our model that we have done, the LOESS model, the smooth model that we've done. And basically here, I'm trying to visualize using the residues. So I got our original data and added the residues here using add residue. And basically I did two graphs. The first one was I plotted the residues against the X values. Then the next one, I plotted the residues against the Y values. And something I want to show you here is that if you see this graph here, the first one is I'm plotting the X values against the residues. And what you're looking at here is, first of all, we're adding a reference line. The reason we're adding a reference line is because the residues should be oscillating around 0. For an unbiased model, the residue sum, positive and negative, should have an average of 0. That's why we want to, for us to check our model, we want to be able to see that our residues actually oscillate around the reference line, which is 0 in this case. So basically here, what you're looking at, if you look at this figure, you want to see whether there is any specific pattern that you can identify from your residues. And so a pattern comes actually with, it can come with experience really. It's not really something so obvious sometimes, but as long as, what I can give you is that, for example, if you have an increasing pattern or reducing pattern, or it comes up, comes down and goes up, then you definitely know that actually there is a pattern in your residues, and your model is doing something which is maybe could be like overfitting or something like that. So you need to do something else. So here, yes, Shamsuddin.
Yeah, so while you were explaining this residue plot, I remember the plot for residue immediately before this exercises. I have a question. I didn't understand it. So please, can you explain the plot for that residue immediately before these exercises in the book?
Yeah, I don't remember that one there.
In the book, use.
In the book, so we go to the book, okay.
Yeah, so, yeah.
Which one was it?
Yeah. Mm-hmm. This one, and the one.
Was it this one?
Yeah, and the one in the upper one.
Okay, so the upper.
Yeah, two of them, they are just residues. So I want to know, what are they saying? I don't understand their meaning.
Yeah, so basically they're doing the same thing. Sometimes it depends on the test and what you're really looking at. So the first one here, this one, the one you see with the frequency polygon, is more of like trying to see the different values of residues, how often they are appearing in your predictions. So basically what you see here is that this is a good model, because most of the residues are 0, and most likely, if most of your residues are 0, then you're really very close to your actual value in terms of prediction.
How do you know most of our residues are 0s?
From here. So here, the residue here, if you look at the value having 0 on the x-axis, because the residues are on the x-axis. So if you look at 0, you see that the count or the number of zeros is the most.
I'm stupid. I don't know. I don't understand this.
No, it's okay.
Yeah, I was looking at it. I don't understand it just now. I mean, yeah, so I understand now. So because where we have the zeros is where we have the highest point, right?
Yeah.
Highest number of stuff. Yeah, I got you.
I mean, you can also do like a histogram if you want.
Okay, right. What about the bottom one?
So now the bottom one, we're changing the idea of the presentation. So we're having the residues on the y-axis and the x-axis and one of the variables, in this case x, on the x-axis. And basically what we're showing is that for how does the model perform for given values of x? How off is it from the actual value, which is y in this case? Is it so much off? Is it so much low? Is it close to 0? So that's what we're showing here. So for example, you could see that, for example, for a value of x equal to 5, you're going to find that the residue can either be, minus 2.6, or could be about, let's say, about, I don't know what value is this, maybe close to 5 also. So kind of spread. But the main thing that we really get from here is not about to look at a specific point. It's about trying to identify whether the model behaves in some kind of pattern. For example, it could be that for values of x, as values of x increase, then the model is actually increasing the residue or the error. Or it could be that as values of x actually become very small, then the residue is actually being big and big also at the same time.
Yeah, so I think based on your explanation, I mean, the polygon one is, I mean, to me, is more intuitive for one to really understand whether we have, the separate of the residue, because, it's more intuitive the way you explained the first one. The second one, one may not really say it is noisy enough. If, I mean,
Yeah, but in just the polygon, when you just look at the distribution, you lose this second dimension. So like the example Alan gave of, let's say, if the errors, the residuals are increasing with increasing x, you wouldn't see that in the first plot. You would only see that with the second plot. Because the first plot, in essence, is one dimension, right? What's the distribution of this one dimension? Whereas in the second one, you can see 2 dimensions, both the residual and the x value at which you see that residual.
Okay, right. Okay. So the first one reason is one dimension is count there, right? Oh, I didn't see that now, how I explain. Maybe I'm blind.
No.
It's basically a histogram drawn as a line.
Yeah, I see. So which one do you think, I mean, you guys' best way to spot residue?
I think that the second one is, oh, sorry, go ahead.
But of course, for me, my preference is I never actually really use the first one here, this one, the frequency polygon. I never really use it. So I always add like a variable. And so some people use X. I don't trust X. You can use X depending on your purpose. So if you're trying to see the relationship, if you're trying to capture the behavior of a certain variable in the data set, then you could use X, of course. But for me, my work is mainly towards prediction. So I actually tend to draw the Y variable on the X-axis instead.
Okay.
Yeah, so it's
thank you, Alan.
It really depends on your purpose, and you can try out different things. It doesn't hurt. All right. So yeah, if we're still on this exploration, looking at the data, so we've talked about the X definitely, and like I said, I always prefer the Y. So here in the X, you see that there is no pattern. The model looks good. Okay, that's nice. But actually, when I did the Y bit, then it became a little bit obvious that the model might not be doing the best part for this. Oh, but on the other hand, if you look at the book, which I actually did,
calendar reminder.
If you look at the LM method, I have it up here, I believe. Yeah, so this is the one for the LM method. And you see the LM method, actually, you could kind of like see a pattern from the Y, if you plot the Y value on the X-axis. But if you go to the smoothing curve that we estimated, actually this kind of pattern, if you just try to remember this pattern now, this kind of pattern actually goes away, tries to be reduced when we do the LOESS modeling, as you see down here. So here the error terms become a little bit distributed and reduce the pattern to some extent. So that's why sometimes you use Y, you can use X, but if you want to do like a prediction, then it might be better to use the Y. because it gives you different views. All right. So the second question for this exercise was about adding prediction, some functions in model R function, model R package. And basically there is add predictions, gather prediction, and spread predictions. How are they different? So what I did all of them just to show you what happens. So add prediction behaves like this. So this one here, add prediction, is the first one we have. So what it does, it adds a column of that model to the data. For each X, Y, for each observation, there is a prediction. But if you do gather prediction, so gather prediction, actually what it does, it does this for each model that you provide it with. So if you have like two models or three models, then it does this for each of the models and concatenates the rows on top of each other. So that's what I did in the third part here. So as you see here, to create a column of the model, then the prediction as it was before. But if we have two models, this is what happens. So you have where did I go here? So you have the first model is SM1 LOS mod. Then the second model is SM1 mod. So what happens is that it first does the prediction, adds the prediction for the first model, which is this one here. Then also later on adds the prediction for the second model, which is SM1 mod. So gather is concatenating. Spread is, well, like you hear in the word, it creates a wide data frame. So I'll show you spread here in the last part. So I'm doing the same here, but with spread. So what it does, it actually puts the predictions as a column for each model. So quite handy depending on what you want to do. So yeah, so now the third question was about geom-ref line, which, you know, the center line, I'll show you here, this one here, the white one. I'm showing it as white here, but I think you can also change the color to something. If you put it here, I'll just try it out just for fun. Let's see. That must be white, right?
Alan.
Yeah.
On the previous one, the gather and spread in tidy bars, are they deprecated or they are still used?
I think they're still used.
Ah, okay.
They still be used. Forgotten that hex code. It's not happening. I have to remember that one. But anyway, you can change the color for this reference line. I've forgotten what thing to use.
In the documentation, it's color with a U. Maybe that's why it didn't work. Although I thought color without the U also works in general.
Yeah, it works both ways. That's weird.
You can try with the U.
Let's see, that would be weird actually. Color, yeah. Let's see, red. Oh yeah, it's happening. Yeah, nice. That's so weird. Yeah. I thought ggplot is, I mean, tidyverse is, you know, both color with a U and without a U.
Yeah, I thought so too. Maybe in this little edge case, they only support the one with U.
Yeah. Oh, cool. I've never thought about that. Like, it's an error. Nice. All right, but basically that's the reference line, you know, and it's part of ggplot2, and basically, why do we display? The reason we display it, as I said before, is because statistically, the mathematics should be that when you're trying to minimize the root mean square error, then the unbiased estimate of the error term should be equal to 0, or the residues, the average of those residues should be equal to 0. So yeah, that's a quick one. Then of course the fourth question was why might you want to look at a frequency polygon of absolute residues? What are the pros and cons compared to looking at the raw residues? And here my answer is, like, if you're looking at it, if I'm looking at it from the prediction perspective, I would want to know, the reason I plot the residues is I would like to know how my model performs when it's trying to estimate a certain value or predict a certain value. So when you're doing predictions, if you are off below and off above, it does not matter. You are off. That's it. So plotting the frequency polygon with minus and positives at the same time, it does not matter to you when you're trying to do that. So what matters is by how much. So the magnitude in this case would actually matter. So if you're trying to do the analysis, or you're trying to observe this from this graph here, at least for me, I try to always look at the negatives. I also try to look at the positives at the same time, which can actually really be a little bit inconveniencing. But however, if you actually take the magnitude, the absolute value instead, then you kind of going to have a very quick overview of how your model is performing, by how much your model is going to be off, either positively or negatively, or either above or below. So that's why doing the absolute residues is much better and just makes more sense compared to having both negative and positive. But however, of course, it doesn't mean that you should always use absolute values, because sometimes you'll find yourself in a situation whereby your model is overestimating everything. So it's going to have like positive residues throughout, or even in other case when you have negative residues. So it might also be worthwhile to see whether your residue plot or frequency plot is kind of skewed to a certain point. So any questions?
None from me.
No, thanks.
All right, so can go to the last part. So the last part was basically about formulas and model families. Not really much of model families, though. Was about how R deals with categorical variables, interactions, and things like that, and transformations, basically. So one quick thing I can show you here is that if you have a data set like this, what R does in the background, this is the data set, so the data frame, which is Y, X1, and X2. If you actually want to do a model that's specified with this formula, Y tilde X1, so what R does, it creates a matrix. And this matrix is the one that is used to do the mathematical computations and things like that. So it actually adds an intercept, and also adds the X variable that you've actually identified. The Y variable is got from somewhere else. But of course, so as you might well know, that you could also do, for example, LM Y, just copy this, Y tilde minus 1 to remove the intercept. And why do you remove the intercept? It depends on your purpose. Sometimes you want to, just remove it because it's not making sense. Most times it's recommended to leave it there, of course. All right. So basically, you can remove the intercept. So I'm trying to show you here. Yes, Samsudin.
Yes, Alan, can you explain again the model matrix, how it works, please?
Yeah. So model matrix is basically just trying to let us, when you have the model y tilde x1, it is the same as y is equal to alpha a plus bx. In this case, a is the intercept.
Mm-hmm.
So mathematically, everything is treated as a matrix and vector. Then you have to do matrix multiplication, blah blah blah. So what R does first is it represents this as a matrix. So model matrix shows you the model, the matrix created by R when you do a formula. So in this case, y tilde x1, when you do that, R gives you that kind of model matrix, this one here, with an intercept, of course.
Okay, so does that mean here when we have this intercept 1, 2, it means we have something like y is equals to 2x plus 1, 2x1 plus 1?
No. So this one here, these are the values of x actually, x1. So from up here, the actual data.
Okay. Okay, I see.
Yeah, but so to finalize this one here, or what the thing that you need to think about is that when you're trying to do like interactions, so in R there's a thing which is also written in the book. I just copied this from the book. Now, when you're dealing with when you're trying to do formulas with asterisks, multiplication, power functions, or minus and stuff like that, then you need to use a special kind of notation to communicate to R that actually this is this is a special function that I want to do. Because if you don't do that, then R is going to kind of like think that everything is actually related to another thing. So in that sense, and R is going to actually try to avoid what they call correlation between variables. So what it does, it drops those variables. So what I can show you here is that if you want to do y tilde, the fourth root of the fourth x1 to the power 4, then R actually does not understand that. So if you do this part here, same data set that we had before. So x1 is 2 and 1. So if you want to have that to the power 4, then you should have 2 times 2 times 2 times 2 times 2, which is I think about 16. And then 1 should be 1. But if you do that, this is what happens. R is actually giving us the same thing as if we are not taking the fourth power of x. So what to do whenever you have something like that, you basically do use an I and put that what you want to do, the computation what you want to do in the brackets. So when you do that, you actually now get the right thing like this. So it's something that you might need to note later on when you want to do some modifications in your data, and you don't want to when you want to do something quick and you don't want to actually do that in the data or in the model before you apply the model estimate yourself. Yes, please.
So what is the purpose of doing this model matrix? Because we are now using it in our model. What is the purpose of doing it?
So it's different things actually you could do. It helps you understand in situations when you, at least for me, when you want to actually do your own model specification. But at the same time, I wouldn't. But I think the most important thing is for you to understand, to make sure that your model is doing the right thing that you want it to do. So in the case, for example, instead of like you writing this one here, y to the power 2, power 3, or power 4, and you think R is doing the right thing, yet it's not doing the right thing,
gotcha.
Then you'll be having wrong results.
Yeah, okay, gotcha. So it allows you just having, if you know the format in which it works, then fine, yeah. All right, thank you.
You could do checks for your model. All right, so now I will do the last exercise, and then we'll see what happens. So let's see this exercise. How many minutes do we have? Okay, 15, around 15 minutes. Yeah, so 4 questions. Let's see. I think we might do about 3. All right. Yeah, so basically here that they are trying to have us play around with the modeling thing more. And they're asking what happens if you repeat the analysis of some simulation data to using a model without an intercept? What happens to the model equation? What happens to the predictions, blah, blah, blah. So just to give you a brief look at this data, sim data 2, it was, I'll show you here. So this is the data whereby X was a categorical variable and Y was, a real number, both positive and negative, and it was a float, basically. And what they're trying to do here was to trying to show some kind of like how R treats this kind of data sets and how we deal with interactions between variables. So one thing here is that if you actually run a simple model of Y tilde X when X is categorical, then and then you do predictions. The predictions are going to give you are going to be the averages of Y within each category of X. So now they're trying to see to tell us like, does this change actually if you remove the intercept? But before I do that, I wanted to show you something that if actually you have this LM function, the linear modeling function, and you do Y tilde 1, basically Y only on the intercept, which is going to be 1, 1, 1, you actually get the average value of Y itself. So I'll show you here. So basically here, the average value of Y is this one here. And when you actually do that silly modeling, then you get the same thing, just something fun to know. Okay, but now to answer the question of what happens when you actually model the Y on a categorical variable, single categorical variable without an intercept, what happens is that if you do something like this, you remove the intercept with -1 and get the coefficient. What happens is that actually the predictions are going to be similar to what we saw before with or without the intercept. So they're going to give us the averages of Y within each category of X. So I think I have it. So what I did first was to get the averages of Y for each category of X. So X has 4 categories, A, B, C, D. And the first one here is for X1, XA is 1.15. So if actually what I do, I did the modeling, then added the predictions to a grid of X. And basically the next thing I did was to visualize. If you skip this one here is the one where I'm trying to calculate the averages of Y within each group. So if you go to the visualization, as we're going to see, let's see if I have that. Yeah. So actually, so basically this is just to show you that this is the coefficients from the model. We have 1.15 for XA. And if you get the means, it's the same thing. 1.15, blah, blah, blah. For B is 8.11. If you go to the coefficients from the model, you still get 8.11, which is basically the same. So you don't even have to go further, but because, well, it's fun to visualize. I also visualize this and I don't know, it was basically the same thing, but the visualizations don't want to tell us anything rather than the values actually. But as you can see, everything is going to be anyway around the average. So this visualization is really useless in this case.
So what's that question getting at then?
Sorry?
I don't understand why they've asked that question then. Is it saying because you're getting the averages, you don't need an intercept?
No. So I think what they're trying to hit at is the fact that normally, of course, it's a silly example having to visualize. To model y on a single categorical variable. That's really quite useless. But in case you have actually now more variables, it means that you might be better off trying to actually do interactions between the variables, the categorical variable and another variable. Because if you don't do the interactions, then the model is going to kind of like only fit towards the categorical variable. In the case that it won't get the patterns that are happening in the data between, for example, one categorical variable and another continuous variable, which does not really lead to a good overview of the data in this case. So I think to me, it was a slow, kind of like a myopic kind of question, because it needed you to actually know the end goal rather than now. Because when you do it right now and just look at it right now, it's like, it's hard to understand what they're really hinting at.
Yeah, right. Okay, thank you.
Cool. And of course, later on, like if we're to do like things like machine learning and you're trying to do like some kind of classification, this might be like important, because like in machine learning, they say that mostly any stupid model is going to actually give you 50% level of prediction without you tuning it. And it's also kind of similar to this, because you actually need to capture more things happening in the data, more interactions, more nonlinearity in the data. Kind of like a similar thing for me when I was doing this, the same thing that I was thinking about. All right. So some questions? Yeah. I don't think there was actually anything new to look at in the other exercises, especially the last one was more still visualization. Do you have any questions? Anything to say?
I think I was stuck on question 2.
Okay. Did I skip it?
Oh, yeah.
Oh, yeah, I skipped it. Oh, oops. Sorry. Use model matrix to explore the equations generated for the models by fitting to this data set and that data set. Why is this asterisk a good shorthand for interaction? So basically, the quick answer for me, was this asterisk is just intuitive from application, just like what the model is doing under the hood. So what you could look at is that if you do the first one with x1 and x2 with addition, this is what the model does. Sim3, yeah. So this is what the model does. So it has x1 like this, and x2, x3, x4, blah, 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 basically. So, but here we have 3 levels of x2 because one is used as the reference always. because if it's not used as a reference, then then we're going to have a collinearity, which is a big problem in statistics, but we don't have to go into the details for it right now. And this is okay, x1 plus x2 is okay. But now if we do interaction, what is happening? So when you do interaction, basically you have this kind of thing, x1 times x2b, then you also have the interaction of x2 times x2c. So basically you have x1 times x2, which is 0, and x1 times x2c, which is 0. So let's pick one which gives us a 1. So here, when you multiply x1 times x2b, then you're going to have a 1, because 1 times 1 is equal to 1. But the rest are going to be 0 because, well, they have zeros here for that row. So simply, this interaction thing is just to communicate that actually it's just the intuition that we want to do multiplication to signify, or to whenever we want to capture interactions. So we can also just use it in the formulation. Did you get that?
Sort of.
Sorry?
Sort of. So when it's saying why is the multipliers a good shorthand for interaction?
Sorry?
When it's saying why is the asterisk a good shorthand for interaction?
Yeah, because it is more of like that's what we want to do when we're considering interactions. So when we're considering interactions, we're doing multiplications of each combination of the variables.
Right. Okay.
Yeah. So yeah. So in this case, it's gonna be x1, each value of x1 multiplied by each of the categories. Let me say categories for the categorical variable. Just that each categorical variable is actually turned into a one hot encoding, which is 1 zeros. More, I think the best term to use is indicator variable in this case.
Okay.
So it's yeah, still not a fun question. But yeah, so I also tried out different things which get really messy with the continuous variables, because then you have then your data set grows really big for all different combinations. All right. Yeah, I think we can end there. There was part 3, I mean number 3 and number 4. Which number 3 was some kind of like writing a function. Wasn't fun. I haven't tested it because actually I got some. Did I get errors? Oh, it works actually. Yeah, but it's not. I haven't really debugged it, so I'm not so sure about what it's producing. Yeah, but then number 4 was about doing more visualization and stuff like that, to try to compare 2 models and see what's really happening. And I did that, but both models seem to be doing a bad job actually. Though I did it on the Y, I plotted on the Y. So, I mean, like I said, I'm biased towards prediction. I'm always trying to do prediction. So this is really a bad model. If you see like, this is a way to identify the pattern, like there's definitely a pattern, an increasing pattern for given values of Y. So bad models, doesn't really matter whether one is doing a better job than the other. You should throw them out. Yeah, I think that's all I wanted to say actually. I don't know, do you guys have some questions, some things to discuss?
I just want to say thank you, Alan.
Oh yeah, you're welcome.
Yeah, nothing in particular from me as well. I wonder if like doing some real world exercises would be useful here, or if we leave that like individual thing. Because like, especially in the iteration chapter as well, I found using some real world data quite helpful. Yeah, but I think the exercises in this chapter, like the simulation data, was a little bit more, maybe, I don't know, closer to the real world. So if everyone's interested, like, I'm happy to skip. Otherwise, I think it could be quite useful to spend time with like fitting a few models.
So can we find some real world examples so that we can try to see them maybe for next year or other? I think the How suggestion is quite good to see how you can apply the what we have learned in real example, and that helps to nail down the concept.
Yeah, I'm fine with I'm fine with either.
Even only an example, I think it's okay. Even one.
Yeah, I mean, I'm fine, of course, because this is simulated data and everything looks good and stuff like that. Of course, I agree that actually it really tried a good. They did really great. Give me a second.